Alrighty. Don't have the test finished yet. Sorry about that. I planned to have them today. I ran out here Friday and forgot them, so I didn't get to finish them over the weekend. So I'll get them. They should be posted sometime tomorrow on Canvas, and then you'll get to see them Wednesday. As far as masking here, just do whatever you're comfortable with. You don't have to wear one. If you want to wear one, that's fine. So we'll just go with that. So if you've had class already, and you probably got the email too, but starting Saturday, it's optional in the hallways and all that. And you don't have to wear them if you don't want to. In the classrooms, it's up to your teacher. So in here, we'll just wear one if you want to. Don't wear one if you don't. Let's see. Okay. The lecture for 3.2 is short. Okay. All we're doing in 3.2 is we are picking up 2 more differentiation rules, okay, 2 more derivative rules. One's called the product rule, the other one's called the quotient rule. So what I would like to do to start with is let's work some more examples of using the power rule that we did on Friday. And then we'll come back to this and add in the product and quotient rules. So let's do some more power rule examples. So some of these we've already done some that were similar, but it didn't hurt to look back at them. So remember our power rule says if we want to take the derivative of x to some power, as long as n is a real number, and then we get n x to the n minus 1. Our power rule. And then we have the sum and difference rules, which says if you want the sum, or if you want the derivative of a sum, you can take the sum of the derivatives, so we can split it up at the plus signs or minus signs with the sum and difference rule. And then we also have the constant multiple rule. It says if you have a constant multiplied by a function, you can wait and find the derivative first and then multiply by the constant. With the power rule, that doesn't really, it's almost easier to just not think about it with the power rule. That is one of our tools so far. So on this one, we want the derivative. We're taking it one term at a time. So what would we get when we take the derivative of the 2t to the third part? Yeah, so we do 3 times the 2 and get 6, and then subtract 1 from the exponent, 6t squared. And then the next piece, minus 6t. Yeah. 2 times negative 3 gives us a negative 6. Subtract 1, we get t to the first power. And then what about the last one? We just have minus 4t. Yeah, just minus 4. The details behind what's going on that last one, we would have exponent of 1, right? So we'd have 1 times minus 4, so we would get minus 4. And then when we subtract 1, we get t to the 0. Anything to the 0 power is just 1. So we just get minus 4. We don't have to think that hard every time. You can just remember if you have a coefficient in front of just a linear variable, just get the coefficient. Let's see. Do another one. What if I have one like this? I want G prime. Right now, where we're at as far as the knowledge we're supposed to have, in order to do this derivative, we're kind of stuck the way it's written. Because it's written x squared times 1 minus 2x. We haven't talked about how to do that yet. We will in just a few minutes. Okay. But we do have another way we can attack that thing. What could we do? Okay. Yeah, we just distribute. So we'll have x squared minus 2x to the third. That's not g prime, that's g. And then to actually find the derivative, we can use our power rule. So multiply the 2 out front, subtract 1 from the exponent. And 3 times negative 2 gives us negative 6. 3 minus 1. Derivative there. We'll talk about another way we can do that one. Because we're going to get the product rule, how to do the derivative of a product. But on one like this, where it just takes, a couple seconds to multiply it out, doing that, multiplying out when you can, and then taking the derivative with the power rule, sometimes it's still the best way, even after we talk about the product rule here shortly. That one like this. I said f of x and use t. That's 3/4 power there, negative 3/4. So, want the derivative of that one. What do we do? Same thing, it just has the fraction involved. We got negative 3/4 is our exponent. So we do negative 3/4 times 2. 1 second. So yeah, that's right. That is right. As a fraction, okay. You just multiply the 2 times the numerator. So you get negative 6/4 t. And then subtract 1 from the exponent. So 1 here is going to look like 4/4. So we'll get negative 7/4. And then we could simplify our coefficient. Nothing wrong with that. Written just like that. Usually, unless we have a good reason to get rid of the negative exponent, we'll just leave it. A good reason would be like, we need to evaluate this thing at 2, something like that. Then some calculators are better than others, but at doing it with a negative exponent, just might want to rewrite it then. Let's see. Oh, we did one like this on Friday. What can we do here? We have a quotient. Right? We got 5 divided by r to the third. We will be able to do this with our quotient rule that we're going to look at in a minute, but it may not be the best way. The best way probably is the way we're going to do it now. We can rewrite it somehow. So I can use the power rule. Do you remember? Yeah, we make it a negative exponent and move it up to the top. Then we can use the power rule. we would do negative 3 times 5, get negative 15. And you do have to be a little careful with the signs. We have to subtract 1, so minus 4. Or you could get rid of the negative exponent if you really wanted to in the answer. Either one. What variable did I use? This one we got 4th root of t minus 4 e to the t. A couple of things going on this one. We got to remember what to do with radicals, and then let's refresh our memory with e to the x. We want the derivative of e to the x. What's it going to be? The easiest one to remember. Oh, the e to the x. So the 4th root part we need to deal with. We need to write it in exponent form. So what would that be? It would be t to the 1/4. 1/4. The index goes in the numerator. I mean, in the denominator. So haven't done anything but rewrite so far. So then when we take the derivative, we have 1/4 t, and then we have to subtract 1. So with a common denominator, that's minus 4 over 4. 1 minus 4 gives us, negative 3/4. And then with the e, you really can think about the constant multiple rule, because we want to take the derivative of e to the t, and then we'll just multiply it by the constant. So the derivative of e to the t is just e to the t. And we had a constant of negative 4 in front, so we'll multiply it by that negative 4. Same thing. Minus 4e to the t. All right, one more for the fraction haters. Should have used different denominators so we got more practice. So we take derivative and multiply by the exponent, so that's 5/3 x. Subtract 1 from the exponent, so what are we going to get on that one? 2/3. And then multiply the next one by 2/3. Subtract 1 from the exponent, what we get? Negative 1/3. There's our power rule. More examples of those. It might not seem like you would end up with this mess, this x to the 5/3 minus x to the 2/3 mess as often, but the way it comes up, remember, in radical form, would be the cube root of x to the 5th minus cube root squared. So that maybe you could see that would not be that hard to come up with. Right? We're having to take the cube root of both sides of something, and okay, all right. So that's a little bit more power rule. And we'll get into product and quotient rules. Product and quotient rules. That's what 3.2 is all about. Okay. And really, we could really do this section in 2 slides. I could have a slide with the product rule and a slide with the quotient rule. We'll look at it a little closer than that. But it's short section. And then we'll just do some more examples. But that's really where you learn how to use these things, is by looking at the different ways you can apply them. So start with the product rule. We kind of pointed this out last time, I think. Maybe we did, I don't know. It was Friday, was a long time ago. So let's think about, we have 2 functions. So one is x, one is x squared. If you multiply them together, you would get x cubed. X times x squared, you get x cubed. But if you think about using the power rule separately, if you take the derivative of x, we'll get 1. If we take the derivative of x squared, we'll get 2x. Down here, if you try to do the power rule on x cubed, you'll get 3x squared. But what would we get if we multiplied these two together? We would get 2x, right? So doing it this way, okay, where we take each function, find the derivative, and multiply them together, gives us a different answer than if we multiply the functions together and then take the derivative. Okay, so with sums and differences, that would work. With products, it doesn't work. So we've got to look at what to do. The textbook tries to give us this idea of thinking about doing f of x times g of x and thinking about the area of a rectangle, and then tries to justify why we get the product rule the way we do. It's just kind of garbage, really. It's trying to build your intuition using a rectangle, but that's really, it just doesn't work well, I don't think. If you want to prove, they're not proving the product rule here. They're just trying to give you like an intuitive idea of what's going on, and to me it doesn't really work well. If you want to prove the product rule, we have to, one way is for us to go back to the limit definition. Go back to the limit definition of a derivative and do it from there. Let's just get to the part where we look at the product rule here. Now you can look at that if you want to and decide if that helps any. Here's the product rule. Okay? It says if we want the derivative of a product, so f times g, we just restate f, and then we multiply that by the derivative of g, then we have a plus sign, and we restate g and multiply that by the derivative of f. So a shorter way of writing this is if using a different notation. They're using Leibniz notation there. If we use the prime notation, it shortens it up some. So if we want f times g prime, the order they're writing it in would be fg prime plus f prime. So we do one function times the derivative of the other, switch it, and then add those together. The order that I remember it, and when I'm remembering the product rule, I remember it like this. F prime g plus fg prime. So all I'm doing there in my memory is I'm switching f prime and g here. That's okay to do because it's commutative. And then after that, I switch the order of the two terms, which again, addition's commutative, so it's okay to do. The reason why I keep it like this in my memory is because it matches up better with the quotient rule that we'll see in a minute. If you remember it in this order, then you just have to remember just a little bit more to remember the quotient rule. You'll get the same thing either way. There's the product rule. So we'll use it in just a minute. Let's look at if we were doing the limit definition. Okay, messy, you won't ever have to do it. Let's just look at where it comes from. So we want that. So by the limit definition of a derivative, what we would have to find is we would have to have f of x plus h times g of x plus h minus f of x g of x h. Somehow we would have to figure out some way of rewriting some of that so we could find the limit. There's a little trick we can do that helps. The little trick is we're going to add a term in the middle that equals 0. So we're really not adding anything. The thing that we're going to add in the middle is we're going to add another f of x plus h, and then we're going to subtract it as well. That way the net change are at 0. Right? We're really not adding anything. We're adding in those terms. So I'm going to stick that in the middle. Again, you're not going to have to like memorize this proof or anything. And I want to show you where it comes from. So we'll have f of x plus h, g of x plus h. And then I'm going to add my middle term, so plus f of x plus h minus f of x plus h minus f of x g of x. So we haven't changed anything, we'll just change the form that we've written it in. The reason why we do that because now we can factor. The first two terms, we've got f of x plus h in there. So I'm going to do it with a bracket. I'm glad you're not going to have to remember this. Let's see, hang on, I missed something somewhere. One second, you might bail on this. I'm missing a term there somewhere, and instead of you having to watch me figure out, I'll do a little video where if you're interested, you can see. Okay. If not, let's just get back to computation. Sorry about that. Now probably 3/4 of you don't care anyways. There's a product rule. It's kind of a neat proof. Might be interesting. You're gonna remember all the terms. So there's product rules. So let's look at this one. Okay. It says if f of x equals x e to the x, find f prime of x. So let's go over to our scratch paper here. Okay. We want to find f prime. So maybe since we're calling this one f of x, maybe we could write down our product rule a different way. Maybe we could say use u and v or something so we don't get the s mixed up. I think that's the order the text does it in. So here we're thinking about like x being our first function, e to the x being our second function. So we would take the first one, x, write it down, and then we need v prime, so we need the derivative of e to the x. That's e to the x. And plus, we write down the second one, and then we need the derivative of x, 1. Okay. Here's our derivative. We could simplify. I think the text, we could factor out an e to the x, right? So equivalent answer, we could say that's e to the x times x plus 1. No, but you'll get the same credit. Either one's okay. The reason why it's worth looking at that is because what if we want to find the second derivative? So then we should probably actually switch the order of that. X plus 1 times x. Now if we want to find the second derivative, we can just use the product rule again. Okay. So then we would copy down the first one, x plus 1. Take the derivative of the second one, so derivative of e to the x. And then second one times the derivative of the first, so plus e to the x times the derivative of the first one, 1. And then get or we could distribute now. Add it x e to the x plus 2e to the x. And then if we factor one more time, x times x plus 2. That one's just kind of interesting the way it plays out. If you look at that, because our original x times e to the x, first derivative, x plus 1 times e to the x, second derivative, x plus 2 times e to the x. Just kind of a neat one. Product rule there is not a big deal. Kind of an interesting example there. Okay. So that's product rule. Okay. Oh yeah, so what would the nth derivative be? We picked up on the pattern, huh? First derivative was x plus 1 e to the x. Then the second derivative was x plus 2 e to the x. So the nth derivative would be x plus n. You get weird stuff like that with e to the x because it's its own derivative. So. Okay. Let's see here. Let me get my stuff organized here. All right, so that's product rule. You got it written down somewhere? All right. So next, we've got quotient rule. And so that's when we have one function divided by another function. So they go back to referring to their rectangle idea. Okay, I'll leave that in there, and you can look at that if you want to. I don't think it's all that beneficial necessarily, so let's just get to the rule. They're in Leibniz notation again, so it makes this look a little bit messier. What this one's saying, we want the derivative of x over g, f of x over g of x. And we've got g of x itself times the derivative of f of x. This time, big difference, we have a minus. Okay. And then we got f of x times the derivative of g of x. And then on the bottom, we get a weird term. We get g of x squared. G of x squared. And no derivative in the bottom. It's just the square of the bottom one. You do have to be a little bit careful here. We do have something I don't even think they mentioned here, but g of x can't be 0. Our function g of x is a 0 function and doesn't apply. Which I guess that's kind of implied because f of x divided by g of x would be undefined. In the prime notation, I like it because you get kind of all the brackets and stuff out of the way. Okay, so prime notation. We want g f prime minus f g prime over g. So the same formula, just different notation. So the way I remember it is I remember f prime g minus f g prime squared, because we can switch to order that first one. So I remember product rule as f prime g plus f g prime, and then quotient rule f prime g minus f g prime over g squared. You get the same thing, switch in order. Okay. I personally really don't like quotient rule. It can be messy. Yeah, yeah. So you bring up a good point. You bring up a good point. There's no law against having quotient rule and product rule. Because what if we want like that prime? Got a product over in the quotient. So yeah, they can get mixed together. Get mixed together and get messy. Um, so here's the example out of the slides. Let's look at it. Let's walk through it. That's a good math skill all on its own to be able to look at where somebody else has got an answer typed out and follow what they're doing. So they're doing G first, and then they want F prime, top prime, minus the top, the derivative of the bottom, all over the bottom squared. And they work that out, the derivative of x squared plus x minus 2, we get 2x plus 1. And when we take the derivative of x cubed plus 6, we get 3x squared. What happens to the plus 6 part? The constant, so it goes to 0 when we take the derivative of this, right? Okay. And this part is the derivative. Okay. The rest of this is just simplifying, trying to simplify. Okay. So that's really my hang up with quotient rule, is you just have, sometimes you have a ton of simplification to try to do. I'd rather spend time on calculus ideas than calculus. So here we've got FOIL, 2x to the 4th, x cubed, 12x, and plus 6. And then we just distribute on that one. That one's not too bad. We get 3x to the 4th plus 3x squared minus 6x squared. And then they distribute the minus signs, and when they combine like terms, that's what they get. What did they not do as far as simplifying? Yeah, they left this. They left that squared. That's going to be, we might as well, okay? Unless we have a good reason to multiply that out. It's probably going to be in our best interest not to mess with the bottom. Leave it something squared. If we were unfortunate enough that we had to find like second derivative here, then we would have quotient rule we would have to do, because we've got this divided by this. And in that case right now, the only way we would have to find the derivative of the bottom would be to multiply that out. Or, well, no, that's not true. Or, what else could we do to find the derivative of the bottom there? We got x cubed plus 6 squared. We could write it x cubed plus 6 times x cubed plus 6, and then what could we use? Product rule. Product rule. So that one, if you had to find the second derivative, you would get a mix of product and quotient. Sounds ugly. They're not all that bad. All right, so let's do some examples. That's it for the lecture. Okay, just those two rules. Let's do some examples here. So this one we're going to do two ways, because sometimes you have a choice. Now you can either do some algebra on the front end, and then use a power rule, or you could jump straight to doing like the product or the quotient rule. We've had a few problems, like, let me back up here. What do we have? We had this one. So on this one, we could have done the product rule and got the same answer, but we can also multiply it out and then get that same. And so like if we did the product rule on that one instead, and so like that would be U, this would be V. Okay, so we could take the order I do it in. Okay, we could take the derivative of the first one, 2x, times the second one, plus the first one times the derivative of the second one. So what's the derivative of the parentheses there? Minus 2. But then we've got simplification we'd have to do. So we get negative 6x squared plus 2x, or added another order on the other one. You get the same thing. A lot of it boils down to sometimes, right? Sometimes it's really heavily tilted toward you want to do it one way or the other. We'll see some of those. But if you have a choice, you just have to decide, do you want to do your algebra at the beginning and then do the derivative? Or do you want to do the derivative and then do your algebra to simplify? Kind of have to decide which one you prefer. Okay. So this one we're going to do both ways. This is one where we could do the quotient rule, or we could avoid the quotient rule. Okay. So let's do it. Do it without quotient rule first. How could we do that? We need to rewrite. Anytime we have a bunch of terms over one denominator, you can split it up into separate fractions. So that would be x to the fourth over x squared minus 5x to the third over x squared plus square root of x. I'm going to go ahead and write x to the 1/2. We're going to have to do that either way. So then that simplifies to x squared minus 5x plus, what's that last one? The last one's a little bit ugly. What's our rule for exponents? For dividing? Subtract, so 1/2 minus 2, or 1/2 minus 4 over 2, x to the negative 3 over 2. And then we can do power rule, so f prime 2x minus 5 minus 3 over 2 x to the negative 5 over 2. That's one way. Okay. With the quotient rule, this will just help you decide which way you like better when you have a choice. Okay. So if we do the quotient rule, so quotient rule is the order I do it in is u prime v minus u v prime over v squared. So I'm gonna rewrite our function. I'll go ahead and change it x to the 1/2 because we'll need that. Okay. So doing quotient rule, what do we get? So the way I have it written, this would be u. So I need the derivative of the top, 4x cubed minus 15x squared plus 1/2 x to the negative 1/2 times the bottom, x squared, minus the top, we just copy it down, times the derivative of the bottom, 2x, over the bottom squared. That's kind of looking like a monster right now. If we simplify, let's see here. It's not terrible because we're just doing distributive property a couple times. So let's see, that's 4x to the 5th minus 15x 4th plus 1/2. On this one, we've got 2 times minus 1/2. So what do we get there? 2 times negative 1/2 is. We do distributive property on the other one. We've got 2x to the 5th, 10, x to the 4th, plus 2. We've got x to 1 plus 1/2. Oh, wait. Yeah. I'm sorry. You should have said, "Hey, dummy." Yeah. So we're adding, right? We're adding, not multiplying. So minus 1/2 plus 2, okay, is, yeah. Call me out. Call me out. Yeah, that's okay. Yeah. Okay. So now what? We have 4x to the 5th minus 2x to the 5th. So that's 2x to the 5th. Have minus 14x to the 4th minus a negative 10x to the 4th. So that's plus. So we get minus 5x to the 4th. And then 1/2 x to the 3/2 minus 2x to the 3/2. So that'd be minus 3/2 x to the 3/2 over, in this case, it's going to be in our best interest to call it x to the 4th. Then what? Divide everything by x to the 4th. So 2x minus 5. Then we have 3/2 minus 4. That's 8/2. 3 minus 8 would be negative 5. Negative 3/2 x negative 5/2. And I really hope these match. Do they? Which way do you like better, the first way or the second way? Yeah, me too. Me too. So what I do when I'm doing these on my own is if I can avoid the quotient rule, I avoid the quotient rule. Not always possible. Not always possible. And quotient rule's not always as bad either. Not always as bad. If I can avoid the quotient rule, I will. It just means, having to deal with subtracting exponents and things and having to do some algebra. Man, to me, that's just so much nicer to work that one like that. If we did not care that our answer ended up in simplest form, then it's not really all that much worse, right? Like if we're happy with this as our derivative, not that much worse. Let's look at another one. Here's a function. We want the derivative. What could we do? At this point, when we get into these slightly more complicated derivatives, there's more than one correct answer. So what can we do if we want to find the derivative here? Yeah. Those are the two big ones. We could try distributing the e to the x and see if that gets us out of any work. Or we could do the product rule just like it's written. Well, change x square root of x to the 1/2. We're pretty much always going to have to do that. So if you think about distributing, our first term would be x times e to the x. So we're still going to have to do product rule somewhere in there. It's just a different product rule. So on this one, to me, we might as well just go ahead and do the product rule and get it over with. So I would rewrite this as x plus 2x to the 1/2 times e to the x. And then the way I remember, sorry, oh boy, hang on. It'll still be there. The way I remember product rule, u prime v plus uv prime. If you want to remember it in the order the textbook gives it to you, that's fine. So I would need the derivative of that first set of parentheses. So that would be 1 plus, and do power rule. So 1/2 times 2 is 1. X, subtract 1, so we get minus 1/2. And then times my second function. Plus, copy the first one down. And then I need the derivative of e to the x. E to the x. Okay. So that is the derivative. It told us to simplify. What can we do? We could distribute e to the x on both of those, or kind of this one we have a common factor of e to the x. No like terms in there, so I would call that simplified. Other than the negative exponent, we can leave it. The simplification part just depends on what you end up with. So I think WebAssign is okay with that. I'm okay with that. Just to question on that one? Okay, let's see. Do another quotient rule one. This one's not too bad. Quotient rule is not always terrible. It just has potential to be pretty ugly. Okay. All right, so the derivative of the top, 1, times the bottom is e to the x, minus the top is x, times the derivative of the bottom, e to the x, over bottom squared, so e to the x squared. There's our quotient rule. That actually simplifies some. Again, we got an e to the x in common on the top. What happened simplifying that one? Yeah, because this e to the x will cancel with one of these. So we just end up with 1 minus x over e to the x. Again, sometimes simplifying is not as important. A case where it would be really nice, instead of leaving it like this to get to this, is if we have to find the second derivative. Then it's easier to work with this than this because this has product rule involved. Don't always necessarily have to simplify, but sometimes it's really helpful. Let's do a quotient with polynomials where it's not too bad. I don't want to scare you about the quotient rule. It's not always terrible. Okay, so derivative of the top, 2x, times the bottom, minus the top, times the derivative of the bottom, 3x squared, over bottom squared. Not a nightmare, but it's not super simple, but not a nightmare. And maybe you can just multiply the top out here. So let's see, that's 2x to the 4th minus 2x minus 3x to the 4th, 3x squared. Be careful with the minus sign. You got to subtract both of those terms. And then we do have some like terms we can combine on that one. So I would be happy with that. Yeah, if you were to get something where everything falls out just right, where you could factor and get one of these as factored, then you could cancel it. Just in general, it's not like that happens every time or anything. It was just when we had to e to the x, that's a pretty nice function to be working with. So see stuff like that happen. General That's good. Let's do one more. Then we're going to add a little bit. So we want to find tangent and normal lines. Remember what that is. At the point 1, 0. So get the slope of the tangent line, we need the derivative. So we need y prime here. Doing the quotient rule. Bottom won't factor, so that would be nice if it would. And doing the quotient rule, I'm going to take the derivative of the top times the bottom minus the top times the derivative of the bottom, so that's 2x plus 1 over the bottom squared and I'm going to leave it right there. I'm not going to mess with simplifying because all we want is the slope of the tangent line at this point. So what does that mean for all these x's? We get to substitute them for 1. Substitute them for 1. So really we just have some arithmetic on the bottom. So I'm going to write it like this. I'm going to write that we're going to do y prime and evaluate it at x equals 1. So that'll be 2 times 1 is 2. 1 squared is 1 plus 1, 1 minus 1 squared is 1 minus 1. 2 times 1 is 2. All over 1 squared is 1 plus 1 plus 1 squared. So let's see, that's 6 minus what? 0. 1 minus 1, 0. So that whole thing's 0. And on the bottom, we've got 3 squared. So 3 squared is 9. So we get 6 over 9, which is, 2/3. Okay, so that's the slope of our tangent line. So using this point, this slope, we can get the equation of our tangent line. Say y minus 0 equals 2/3 x minus 1. So the slope of the equation of our tangent line, 2/3 x minus 2/3. You remember how we figure out the slope of the normal line? Normal line is the one that comes in perpendicular. Yeah. So that's our normal slope, normal line slope. So to get the equation of our normal line, we use the same point. We won't go through the same point, but different slope. So y minus 0 equals negative 3/2 x minus 1. We get negative 3 over 2x plus 3 over 2. It's our normal line. And it might not feel like much to you because you're just thinking about all the terrible computations you're having to do. But it's really pretty nice. We've come a long way of us being able to take not the friendliest of functions and spend just a couple minutes and be able to get the equation of the tangent line and the normal line at that point. Didn't really have to work all that hard thinking about how much we accomplished. Good to try to keep things in perspective. I know the computations get out of hand as you get in here, but you remember how much you're actually finding. And all right, questions? Good. All right, we'll stop there. We'll do a few more of these next time. If you didn't get on the sign-in sheet, make sure you get on there before you leave. Should have tests to give back to you Wednesday.